to the next lecture on unit number 5, optimal power flow analysis. This is Vishal Maitre from Department of Electrical Engineering, Bharati Vidyapeeth, deemed to be University College of Engineering, Pune. So in the previous lecture, we have studied about the methods that are applicable for the solution of optimal power flow and the methods, usually the gradient method and Newton-Raphson method. We have seen the equations for those method, algorithm, and the best method for going for optimal power flow analysis. Now that was the part we can say part 1 of the unit number 5. Now in the second part we are going to study about the loss sensitivity analysis. Now this loss sensitivity analysis, now you as we have seen in the optimal power flow analysis, we are dealing with the real time analysis. So here the sensitivity factors are going to be important. So now let us see in this particular lecture what are those sensitivity analysis. So here we are going to study this session contents: introduction to sensitivity calculation, loss sensitivity calculation, perturbation method for loss sensitivity. Now perturbation method is the meaning of perturbation is going to be the deviation in the quantities that are related to the loss sensitivity. So out of which we are going to study for the generation shift factor sensitivity, line outage distribution factor, shift factor sensitivity for phase shifter or phase angle, and outage transfer distribution factor. The equations we are going to study and the formulas that we can calculate this sensitivity parameters. And if case you are having any doubt, you can just post your doubt so that I can revert back to you with the solution. So let us start with the sensitivity calculation. Now this sensitivity calculation are very useful for having analysis and implementation of certain parameters, that is loss sensitivity, voltage sensitivity, generator constraint, shift factor, and area based constraint shift factor in practical transmission network. Now these are very important, these four pillars we can say for transmission network to have optimum solution with the calculation of these parameters for sensitivity analysis or calculation. So out of this, in this particular unit, we are going to focus only on loss sensitivity and generation, then generator constraint shift factor, because this voltage sensitivity is beyond the content of this syllabus, and area based constraint shift factor is also beyond the content of this syllabus. So these two factors are also covered in some other subject. We can mention it in power quality also. And then for this loss sensitivity and generator constraint shift factor, we are going to have certain functions. So that function can be a dispatch function for loss calculation, which can be a function of standard market design SMD, such as location based marginal price. And then loss allocation does not affect the generation level of power flow or power flow. It does modify the value of LMP. So only the value is important here. It is not going to affect the power flow values. So the calculation of loss sensitivity is based on one of the distributed slack buses in the energy control center. So this point is very important. We need to have one distributed slack buses. Usually whatever we are having is the usual slack bus that we are considering. Arbitrary slack bus also we can consider, but for this calculation we require a specific distributed slack bus because we are going to obtain the result at that particular bus. So the objective of simultaneous, there is one more test which we call it as simultaneous feasibility test, and that test is to determine whether the network operation is feasible for power flow injection or not at that particular bus. Apart from that, we have one more sensitivity analysis which is going to detect the weak buses or nodes which are having the low voltages for the entire power system. Now let us see the sensitivity calculations that the formula can be elaborated, or we can use that formula for distributed slack bus. Now here there is no need for calculating the new set of sensitivity factors. Whatever we are getting from power flow calculation, that itself we can use it. That we can see in generator shift factors and outage terms that we can consider for that we will see in upcoming slides. So now in particular what we are going to do is loads are going to be selected as the distributed slacks rather than the usual generator slacks. So we can see that we all usually use the generator slack, but here we are going to use the distributed slack for the loads. So the loss sensitivity values will be unchanged no matter how much is the status of AGC unit changes. Now this AGC control is going to be very important because certain changes are made in this AGC control so that the power flow is maintained. This is going to be a part of energy management system which is going to hamper this market design, that is we have seen in previous slide. So for this economic dispatch, optimum economic dispatch of this power formulation can be defined by the function which is going to have an objective of minimization. So minimum function will be the product of CJ and PGI such that the losses or the PD is going to be the real power which is plus losses will be contributing the total generation, and then we are going to have the constraints which are given in equation 3.3, that is summation of multiplication of Sij Pgi will be less than equal to Pmax, and Pg value should be between minimum and maximum, so it belongs to Ng. Now let us see what all these parameters are called as. So where PD is the real power load, Pi max is the maximum requirement of power supply, Pgj is the real power output, Pg min and max are going to be the real power at minimum and maximum real power at bus J. PL is the network losses, Sij is the sensitivity factor with some active constraint. Active constraint, what is the meaning of active constraint? We have seen in previous lecture, you can refer the previous lecture notes for that. Cj is going to be the real power time price for the source, and Kmax is the maximum number of constraint. Now with this we can have this Lagrange's function for those two equations, which is going to be the summation of, we can see that product of this function of the injected power Pi plus Lagrange's multiplier into the active power flowing through them. Note down these sign conventions are followed as per we are following in normal load flow. Let us go to the next slide. Now the loss sensitivity is based on one distributed reference, will keep changing because of the change in AGC unit. Now for AGC unit, when we consider, it is not going to hamper, that is not going to hamper the values when we consider for the reference generator bus. But when we consider the load as distributed unit, then we need to consider the changes in AGC for loss sensitivity values. Note down the difference between the two statements. Thus the distributed load slack is used here to have the sensitivity calculation. It cannot be performed with the normal generator slack bus that we usually have. So the criteria can be selected with the Lagrange's function. We can see here the partial derivative. This is going to be the loss sensitivity factor deba FL by deba PDI. This is going to be the function, and Lagrange's multiplied by the power and equating equal to 0. So this ND is this equation is related to the load side, and the same equation we are having in the generator side. Note down here, this multiplying factor for this load is 1 plus deba PL by deba PDI, and for generator it is deba PL by deba PG minus 1, because it depends upon the value which is greater in case of generator and on the load side. So this LDI value can be calculated by simplifying these equation. We are simplifying, rearranging the term in terms of, if you see equation 3.8, this is Lagrange's multiplier, and in equation 3.9 we have got the equation for LDI. We are rearranging, and then we get the equation for LDI and LGI. So these two terms are very important for the calculation on the load and on the demand side. Load and the generator side, sorry. So these are again the factors which we are considering. Lambda, that is the Lagrange's multiplier, loss sensitivity of the load. So remember, PD is going to be the loss sensitivity for the load, G is going to be the unit. This unit is nothing but the generator unit. So deba PL by deba PI is the loss sensitivity which is going to be for both PDI by deba PGI. PDI and deba PGI. So since distributed buses are used here, all less sensitivity factors are 0. And rather in other generator slack bus, most of the case it is sparse matrix. So here we are having non-zero terms. So let us now select a function pk, which is consider an arbitrary slack bus k, which is now pk will be the function of that power, injected power, and that power we can call it as pi. So note down that n is going to be the number of buses in the system, pi is the power injection at bus I. So pdi and pgi will be the parts which are going to be for the injected power on the generator as well as on the node side. So this point is should be noted that load can be treated as negative generation, because the normal sign conventions which we see for AC load flow can be applicable for this on the load side. So these equations, when we simplify, now that equation 3.9 and 11 which we see here, LDI and LGI, that can be changed to equation 3.13. We can see that Li, this LDI and GI, we are having now generalized term, which we can call it as 1 minus delta PL by PI. So again, we can have the Lagrange's function as we have seen here, the multiplication, the same term we can obtain it here for the number of buses n. Moving on to the next slide, 3.2 equation. Now this 3.2 equations which we have seen, this equation can be modified and written as PL equal to PK plus summation of PI. So this PK is the function of this injected power, and this injected power is the summation of all the buses, power flowing through all the buses. So now here we can define a new Lagrange's function which is represented by this star, which is function of this injected power plus Lagrange's multiplied in this bracket, that will be the power, which is going to be the generated power consumed by the load, and the losses. So please note your sign, this is going to be negative because this is the consumed power which is on the load side. So this optimal criteria which is going to require for having the, considering the Lagrange's function, we have to satisfy this equation. So this equation we are getting the derivative, partial derivative with respect to Pi. So this derivative, partial derivative, when we get this particular equation, and that equation has to be equated equal to 0 to get the optimum function. Now from this equation, if we take the partial derivative with respect to Pi, so we get this term 1 plus delta Pk by delta Pi. So from these two equations, what we are going to get is, we are getting this term, and from this particular term, dFi by dPi into Li star, we get dFk upon dPk. So this is going to be the injected power, and this is the function of injected power which is in the Lagrange's term. So this Lagrange's term we can obtain in this particular equation. Now if you observe this Li which we have obtained, and this Li star is almost similar. Yes, it is almost similar, but there are certain changes. What are the certain changes? That it has a different meaning. Even if the notations are same, it has some different meaning. What is the different meaning? The former, that is Li, will be based on the distributed slack bus, but this Li star which is based, that is for arbitrary slack bus. This difference is very important, though the factors are same. So loss sensitivity on the distributed slack bus is delta PL by delta PI. We are representing it now by ds to avoid the confusion, and for the arbitrary slack bus we are representing by the k, which is always is kth bus is always equal to 0. Now the new Lagrange's multiply Li star, which is going to be for arbitrary slack bus, is actually by Li by Lk, where Lk star is 1. Now from these equations, what we can do is we can simplify this, or we can obtain the value of this loss sensitivity for arbitrary bus k in terms of the distributed slack bus. So this is very important. So these two equations are very important. Note down the equations. Now we can have one incremental set of incremental transmission losses by considering the arbitrary slack bus, which can be calculated by using this formula, delta PL by delta Pi, delta PL by delta Pi ds, that is the distributed slack, minus PL at bus k ds. So this equation is almost like output minus input upon 1 minus losses. So it is same like that equation. So the formula is very simple, it is very effective and accurate for using in real-time energy market. It will avoid the new set of equation by changing the values of the slack bus. It is not going to change, it is not going to update its value, it is going to be fixed, so that computational time is required, and we can converge at a faster rate to the optimum solution. No matter, even if there is a change in AGC, that is automatic generation control, still these factors are not going to change. That is the you can say the benefit of this particular system. Now let us see the various perturbation method that are going to be implemented for loss sensitivity. Now note down these two steps that we are going to use in most of the cases, step 1 and 2. So in step 1, what we are going to do is we are going to perform the power flow calculation. As I've mentioned, whatever the calculations we are obtaining it from the normal load flow, most of the cases we are going to use as an input in these calculations. So let us see for loss sensitivity. In first step, we are going to obtain the initial system loss from the normal load flow. In the second step, we are going to have the calculation for sensitivity with respect to generator. In that case, what we are going to do, we are going to increase the power of the generator, that is delta PGI, and we are going to allow the slack bus unit to absorb the same amount of power that is generated by bus I. So whatever is the generated, the same is going to be consumed by that particular slack bus. Now run the load flow again. Now get the new system losses, we are going to denote as PL. So now for unit loss sensitivity, we can get the difference PL minus PL naught upon delta PI, and for load sensitivity, note the difference, only this delta PGI changes to delta PDK. So note down, when we are calculating the difference, this difference is nothing but we are going to calculate the deviation which is there between the actual losses between the two conditions. That is why it is called as perturbation method. Let us see the next, that is generator shift factor sensitivity. We call it as GSF. Now here again, what we are going to do is we are going to choose a generating unit I and a branch constraint J. Then we are going to perform the power flow calculation and obtain the initial condition Pj naught. Now Pj naught we are using, naught is always used for the initial condition that is obtained for the normal load flow. Simulate the calculation with respect to branch J with respect to generator I. Now we are going to increase the power of the generator I. The slack bus will absorb the same amount of power. Now again run the load flow. Now get the new set of power flow, new value of power flow, the net power flow. Now take the difference between Pj minus Pj naught upon delta Pgi. So this is going to be the generator shift sensitivity factor. Always consider that it is the calculation steps are similar like the previous step, this loss sensitivity, and only note the last point which is important, that load should be considered in as the negative generation, then only this is going to be possible. The next factor that is there, the line outage distribution factor. Now in this line outage distribution factor, instead of considering a generating unit, we are going to consider a branch or a line. So choose a branch L that is going to be simulated as outage due to some reason. Out of one power system, suppose there are 10 buses, we are removing one as outage, that branch, and then we are going to perform the analysis for that particular branch, and constraint J is there. Perform power flow calculation by branch before branch L is open. Obtain the initial power flow Pj naught for the branch J and PL naught for the branch L. So we are calculating the two powers for the two branches Pj naught and Pjl. Now simulate the calculation of LODF. Open the branch L while the unit power and other load remains unchanged. We don't have to change. Only we can do is we can do it again, run the load flow. Now you can get the power flow at bus J only, because bus J is now in the system. But as branch L is not there in the system, it is out for maintenance or some other reason, the power flowing through it will be 0. So that we can easily calculate the value of LODF, which is going to be Pj minus Pj naught upon PL naught. So this is going to be the line outage distribution factor. Similarly, next we are going to study about the phase shifter. Now this phase shifter is by changing the tap position or by changing the susceptance of the phase shifter. So one thing we are going to do is we are going to choose a phase shifter T. The notations are considered different for the branch with branch constraint J. Perform power flow calculation and obtain the initial power flow Pj naught. As I have mentioned, first two steps are almost similar. Simulate the calculation of shift factor with respect to phase shifter T. Increase the taps of the shifter, that is delta T, or by changing the angle delta theta T. So simulate, we can initialize this by changing the values of susceptance of the phase shifter, run the load flow and get the values of at the branch J. Then compute this shift factor sensitivity for shift phase shifter. So we can have either in terms of this phase shifter, taps of the phase shifter, or in terms of angle. So we can have the two equations in any form we can want. And the last is going to be the outage transfer distribution factor. Now in this again also we are going to consider a generating unit I, a branch L that is to be simulated as outage, and a branch constraint J. Now note that whatever we have studied in this GSF and LODF, it is going to be the combination of this in OTDF. So we are going to have a unit and a branch. Now initially we are going to perform the power flow calculation before the branch L is open and obtain the initial condition for the power flow at branch J and PL as PL naught for the branch L. So first of all, what we are going to do is we are going to calculate the GSF with branch J and L with respect to the generator I. Increase the power for the generator I, and the slack generator should absorb the same amount of power. Now conduct the power flow calculation and get the net power flow for the branch J and PL. Now here we get the value of GSF. As I mentioned that we are going to divide into GSF and LODF. So this is the step for GSF. These equations are similar as we have studied in GSF also. Now after that we are going to simulate the calculation for branch J with respect to branch outage of branch L. We are going to have the outage for branch L, open branch L while the unit power and load remains unchanged. So these steps are similar to LODF. Note down, that GSF and LODF is combined, we are going to get the sensitivity for OTDF. Only there is slight change in the formula. OTDF is going to be calculated by summation of GSF plus LODF, product of LODF and GSF. So this is going to be the outage transfer distribution factor. So it is called outage transfer. Outage is for the line outage and transfer is for the power transfer that is going to be considered. So that is why we are going to go for this particular method. So these are the 3 to 4 methods that are considered for sensitivity analysis. So hope you have understood. That's it for this particular lecture. In the next lecture, what we are going to cover is the remaining part of unit number 5. Apart from this, whatever are the methods that I have mentioned, there are 2 more methods remaining in this particular unit, but that is beyond the scope of the syllabus. That is why we are not considered. So in the next lecture, we are going to study about the economic dispatch with considering this loss formula or the sensitivity factors and the linear programming method. That is only the part which is remaining from unit number 5 that we will see in next lecture. Thank you.